Alright, so welcome to the 2 integer sum 2. This question is actually an altered version of the 2-sum easy Neetcode problem. So basically, they want the indexes of two numbers that add up to a given target. So what's changed here? So just like the original problem, we want two indices, index 1 and 2, where if you grab the number at index 1 and the number at index 2, they add up to a target. So that's kind of the same. Now the biggest difference is that the array is sorted. So before it was a non-sorted array, and now it's a sorted array. It's sorted in a non-decreasing order, which just means that the next number is either equivalent to the previous number or larger. Something like this would count. Because if you say ascending, then it's strictly like this. But with a blessing comes a curse. Our curse is that it uses O1 space. So we're not allowed to use a hash map, if you remember, because that's a solution that required an O of n extra space. So we'll have to think of something different. But because the list is sorted, we can take advantage of the two pointers algorithm. In my last video with the valid palindromes, we were also using two pointers. They basically started at the end and then started working their way inwards. It's the same concept here, but the application is a little bit different. So let's take the first example earlier, 1, 2, 3, 4, and target is 3. So if I create two variables, well, two pointers, one is L and one is R, and L points to the first index and R points to the last index, we can do something pretty interesting. Now we can add up the values at L and R, so 1 plus 4, right? And then there's actually three possibilities here. So one possibility is that the sum is smaller than target. Possibility 2 is that sum is greater than target, which is this case because 1 plus 4 will add up to 5. And the third case is that the sum is the same as target. If we've achieved the third case, then we can just return the indexes and call it a day. But in the other two cases, then this is where we apply the two pointers algorithm. So in this problem, it goes something like this. If the sum is larger than the target, like it is here, then we want to move the R down by 1. Why do we move the R down by 1? Well, that's because this array is sorted. When we shift R to the left, we're going to find a number that's smaller or a number that's equal to it. Because remember, it's non-descending, right? So in this case, we move R to the left by 1, and then we check again. What's 1 plus 3? Well, the sum is 4, and 4 is still larger than 3. So we apply the same algorithm, and then we move the R to the left one more time. And that's our answer, 1 and 2. And by taking advantage of the fact that it's sorted, we have a mechanism that will search for the relevant pairs efficiently. Let's look for another example. Let's say our target is 6 now. Then what happens? Well, same thing, L and R starts here. And when we compare, what's 1 plus 4? Well, that's 5. And 5 is in this case where it's smaller than 6. So what happens here is that we move L up, because when you move L to the right, the next number is never smaller than 1. So the next number will at least be equal or greater. And in this case, we got a number that's greater. So now we found our indexes. So that's pretty straightforward. So let's say I change the input a little bit. So because before we had a strictly ascending input, now we have an actual non-descending input. So you have stuff that's like this, right? So if you want to look for the 6, well, the algorithm works exactly the same. That's this and this. It's too small, shift it up, too small, shift it up, too small, until we get our answer. So we don't actually need to do anything special if the input is not strictly ascending. And that's pretty much it. It's a pretty simple algorithm. Let's code it up. All right, so we're going to create two variables, two pointers, L and R, which is going to point to the start of the input list and the end of the input list. Once we have that, we want to write a while loop while L is less than R. So if L has crossed R, then we stop searching. So to be honest, if I wrote while true, I think this would have been the same thing. Since this question guarantees a solution, the exit condition of the loop doesn't really matter. But in these kinds of two pointers algorithms, it's pretty common to stop like once the indexes have crossed over or it's pointing at the same index. So I'm just going to leave it like this just for familiarity's sake. But you can definitely write while true if you really want to, because you must have found a solution before the search is over. Anyways, we're going to add up the values at L and R. So I'm going to say total is equal to L numbers L plus numbers R. So if we say that the total is equal to target, then, well, oh, I forgot the if. Then, well, you just return the results, right? And what do we want? We want the indexes, the one indexed indices of L and R. So it's just L plus 1 and R plus 1, right? Because typically this is 0 index. After that, the other case is if the total is less than the target, I want to move the L pointer up by 1. And in the last case, where it's larger than the target, I want to decrement the R pointer by 1. And I think that's about it. Because the question guarantees exactly one valid solution, so we don't have to handle the case where there's no solutions or multiple solutions. So let's hit it. There you go. Pretty cool. And the time complexity for this thing is, well, running the 2 pointers algorithm means that we're going to be touching every element at most once. Worst case, we go through every element inside the input list. So we'll say time complexity is O of n. And space complexity, we're not using any extra space besides like these variables, which is O1. So O1, O1 time, and O1 space. And again, I just want to reiterate that this is really only possible because the array is sorted. If it weren't sorted, then this wouldn't work. Okay, bye.